Okay, so I think we can start. So in the last lecture, we started reviewing the basic machine learning tools just as a recap, with the idea that that will be helpful for us going ahead as we go into uh, deep learning, right? That is what we are doing. And what we primarily did last time was kind of discuss supervised learning, unsupervised learning, reinforcement learning, and primarily that is what we did. We started with linear regression, but we did not really finish it. I went very fast, and as I said last time, we will start with linear regression today, which will basically complete the review part, and from linear regression we will transition to neural network, which is basically the main engine of this course on deep learning. So that is, so for today the plan is to complete our discussion on linear regression and then transition to neural network, neuron models, and so on and so forth, which will form the foundation for deep learning, right? So with that, let us start. So lecture 3, and we are going to continue with review of machine learning for now, and in particular we are going to review linear regression, right? So linear regression, I mean, if we talk about the objective, in any machine learning method we have data to start with. So the objective is given data, I want to learn the mapping between the variables. So given data, comma yi, we want to learn mapping from x to y. Okay. So given, I mean, this is again, this is not about linear regression, this is about regression in general. So this objective has nothing to do with linear regression. This is objective in regression, or even classification, supervised learning in general, right, where y is classes, right. So now in linear regression, we represent the mapping as, so I have y and we represent it as a0 phi 0 of x plus a1 phi 1 of x plus a p phi p of x. What is phi here? Basis, right, we talked about last time. X is my input variable, potentially a vector, y is my output, and a0, a1, a0, these are my parameters. What is a0? Bias. Phi naught will become 1, so bias. And a1 to a p, those are my weights. In general, we will be referring to them as parameters of my model, right. Now, obviously, we will not write in this form, I mean, we will rather prefer to write it in a form such as okay. We will be writing it using the vector notation, which will be of this form, where a is the weight vector or parameter vector. A goes from as you can see 0 to p, so there are p plus 1 dimensional vector. Phi is my basis function vector, which also goes from 0 to p, so p plus 1, and we do an inner product to get my y. Okay. So this is the modeling assumption that is there in linear regression. So in linear regression, this is my modeling assumption, and I will be using it later. So let me write it as equation 1, because we will be using it later. Okay. Now remember that we have data, right? Now this expression, if I substitute this data, I can write it in terms of data as well. In general, this model has nothing to do with data. This is the relation between x and y that we are assuming, right? So this is the relation between x and y that we are assuming, but the idea is we want this model to satisfy the the data that I have, and by satisfying it, somehow we want to estimate this parameters. So that we should keep in mind, right? So using data, the data set I have, we can write y. Y is now a vector. How many elements? N. N data point, n elements, right? Is equal to phi. Now this is capital phi, and this is a matrix, okay, times A. A remains the same, it is a vector as before, okay. So what is the difference between equation 1 and this equation? Equation 1 was for a generic x, this one is for the training data only, and that is why your phi, which was a vector, has become a matrix, and y, which is a scalar, has become a vector, and A has nothing changes, A remains a vector, because those are the parameters. So just for completeness, I mean, how will these things look? Let me write it down. So y will be of this form, right? I have my y 1, y 2, and it will go up to y n. So I have this n data point, so right, and it's a n dimensional vector. Okay, it's a n dimensional vector. Then there is this phi, which will, so how will phi look like? Let us write down. So I have my phi 0, phi 0, phi 0 evaluated at x 1, phi 0 evaluated at x 2, sorry, x 1, and then not, this is phi 1, wait, phi 1 evaluated at x 1, and ultimately the last one is phi p evaluated at x 1. The next one will be phi, what will be the next thing? Phi 0 evaluated at x 2, phi 1 evaluated at x 2, phi p evaluated at x 2, and I am not writing the other, but you know what will happen. It will go up to n. Each row is representing one data, each column is representing one basis. So what is the dimension of this thing? N cross p plus 1. I mean, yeah, it's easy to miss that one. We start because the bias term is there, right? A, but before A, let me also write the whole data pointing. So, there is a data matrix also, by the way. So, if I write my data matrix, is simple. I have my x11, x21, xk1, x12, x22, xk2, and then you go like that, x1 n, x2 n, xk n. And this belongs to n cross k. The reason I wrote the x, the data matrix, is because, or to rather to establish that the number of k, the number of feature, need not be equal to the number of basis function. So, so that you are clear and we are on the same page, do not think that the number of feature is equal to the number of basis vectors. The number of basis vectors is something you will select in most cases. The number of features is something that will be given to you in form of data. So, you will have not control over that. You will have not control over how many features you have to work with, but you will have control over how many basis function you decide to select. And in fact, I mean, we will later come to that, but that will form some basis for going into neural networks later in some loose sense. Okay. A I am not writing, but that is also the A vector. How will it look? A0, A1, dot 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 AP. So, A vector will be p plus 1 dimensional vector. So, A will be, I mean, I am not writing the A, but I am just writing this one, it will be p plus 1 dimensional vector. Okay. This matrix has a name. Can someone tell me what is the name of this matrix? This has a name? Design matrix. So, this matrix is known as the design matrix. So, if you hear the term design matrix, this should come into your mind. Any idea when design matrix will become similar as a data matrix? Linear. Linear model, and the bias is, excuse me. Okay. So, yeah. So, when the you ignore the bias for now, let us say, and you are only working with a linear model. So, whatever the feature is there, you are working with that, no transformation, no non-linearity, nothing. So, it becomes linear also in the feature space. Remember, I told last time that linear regression is linear in the parameter space. It is not linear in the feature space. This two will be same when it is also linear in the feature space. Kind of obvious. Okay. So, we started talking about it. By the way, this is the first step, or rather second step of linear regression. In general, you can also think about machine learning. The first step is data collection, right? Assuming the data is given to you, that is step 1, you do not have to do. This becomes your step 2, which is model selection. You are deciding how you want to model. Okay. So, this is step, yeah, go ahead. P plus 1, yeah, yeah. I mean, cross 1 I am not writing because vector, but p plus 1, yeah, right, thank you. Yes. Okay. Yeah. So, this is the first step. But to use this model, I mean, remember what is the goal of regression or supervised learning in general? The goal is not to learn the model. The goal is to have a model that can help you in making predictions for new inputs for which y is not known. That is the goal. If that is the goal, what is missing here? A is missing because A I do not know. So, naturally the step 3 will be finding A. Step 1, collecting data. Step 2, selecting or deciding on your model. Step 3, training the model, which means finding A. And step 4 is now deploying and prediction, obviously. Okay. So, we are still now in the step 2. Okay. Moving ahead in step 3, right. So, step 3 is training the model, okay, which is basically estimating A. So, this is my step 3. Remember last time I said that for estimating or predicting, in this case estimation is the correct term. So, for training the model, what do we define? What do we need? Loss functions, right. So, for training, the idea is that we define a loss function, and loss function is a function that maps your prediction to some statistical error in some sense, right. So, it is a function that takes your prediction as an input and obviously true labels also, and it maps these two things to a error metric in some sense, some statistical error. Okay. We define a loss function. This is for training. And now, common loss functions I was writing last time, let me write again. LA 1 by n summation over I equal to 1 to n yi minus A transpose phi of xi square. Okay. What is this loss function? Mean squared, right, or L2 loss. I mean, also call it L2 loss, but mean squared. I also wrote this one last time, so I will repeat it again. The L1, so 1 by n summation over I modulus of yi minus A transpose phi xi. Okay. So, this is my L1 loss. Any other loss you are aware of? These two are the obvious one. I am guessing apart from those who have done nothing on machine learning, everyone else was aware of these two laws. But is there any other loss you are aware of? Hmm? Cross entropy, yes, that is used for classification. Louder? Yes. There is also Hoover, that is a robust loss. And in general, depending on what, I mean, okay, I will not go in that direction, but there is this concept of likelihood, and from there you can come to losses. But for this course, right now we will not go into likelihood. So, think about only loss function, forget about likelihood for now.
This one comes from likelihood, right?
Yes.
We take the noise as Gaussian then.
Yes. The first one is mean square is related to Gaussian likelihood, the second one is to Laplace. So, both of this comes from likelihood, but we will not go into there that we will not go into that direction right now. We will probably go into that direction for any in the middle of the course. We have done transformer and we now want to learn something generative. So, at that point I will probably introduce that topic. For this course, I think this is sufficient for now at least. Okay. So, we define loss L2, L1, Hoover, cross entropy, binary cross entropy. So, there are different losses. And now what do we do with this loss? Minimize. So, once we have defined the loss, the next sub step is A star is equal to arg mean. So, you want to minimize L of A. Okay. And now, how you minimize this problem depends on how you are training the model. So, there are broadly speaking, there are two ways of solving this optimization problem. So, training can be done using two methods. I am not saying both will always be applicable. The first one, the easiest one is you will take the derivative of this, equate it to 0, solve it analytically. The obvious one that we study in our school, right, that equate the gradient to 0, solve that equation analytically. if you can, and that gives you the optima. Obviously, we need to check the second derivative to see whether it is a minima or maxima, but that's there. Okay. The problem, however, is that you will not be always able to solve this analytically. In many cases, this loss will be very complex, that the derivative of this loss will be highly complex, and there will be no analytical solution. There might be multiple solutions also. That takes us to the concept of local optima, non-convex function, right? And in that case, you go with some numerical optimization scheme, and that is the indirect method. In neural network, in deep learning, the indirect method is our only method. We do not have a choice, to be very honest. With neural network, you will see later that analytical solution is out of the picture. So, we will be working with indirect method only, but you should know that there is also this notion of solving it directly. For example, in least square linear regression, you can actually solve it directly. Okay. So, there are two ways of solving. Let us call it equation 2, and these two methods are direct approach and indirect approach. Okay. So, there are two ways of solving equation 2, direct and indirect. As I said, in direct approach, solve equation 2 analytically. Okay. That means you take the derivative, equate it to 0 and come up with an analytical solution. The problem, however, is that not always possible. The problem, however, is that not always possible. Okay. It exists, but not always possible. When is it possible? Example. So, for example, we can use direct approach for linear regression with L2 loss. We can use direct approach if we are using linear regression. Linear regression is that means my design matrix, it will be like equation 1, right? And I am combining it with this first loss function, right, that you are seeing. So, if I do that, then it is possible. And what will be the solution in this case? I will also give you that. You can derive it. I am not deriving it, but you can derive it. It is pretty simple. And in this case, the solution comes out to be, anyone knows what is the solution? Phi, in terms of phi, you are right. So, yeah, phi transpose phi whole inverse, that is the pseudo inverse actually in some sense, I mean multiplied by phi transpose y. So, phi transpose phi inverse phi transpose, that is like pseudo inverse multiplied by y. So, this comes out to be phi transpose phi, and keep in mind, I mean keep a note which phi I am writing. It is the design matrix, because we are training from the training data. Inverse phi transpose y. These are all matrix. This is a vector. Okay. You should derive it, but on your own. But yeah, this is what, this is a direct approach, an analytical solution that you get for linear regression with L2 loss. Okay. The other option is indirect approach. And as I said, in this case, we solve equation 2 using numerical optimization. Numerical optimization. Now you can use, I mean, optimization is a subject of its own. Some of you have done that course. Even those who have not done that course, I am pretty sure you have some fundamental idea of optimization. So, and if optimization is a course of its own, it is not possible that there is only one numerical optimization scheme. There are series of numerical optimization algorithms, right? First order, second order, Newton's is for example one example, and then gradient based, gradient free, you can do it in that manner also. Brute force is also there in some sense, and so on and so forth. Now, in machine learning generally, when you are using this numerical optimization, it is generally restricted to first order. I will not say always, there have been recent work where second order optimizers have been used and are found to yield better result, which is not surprising, that is why it is second order. But in neural network, in deep learning, for this course, we will restrict ourselves to first order optimizers. And the reason is that you will hear about gradient descent, stochastic gradient descent, Adam W, RMS prop, AdaGrad. So, these are the optimizers we will cover in this course, and all of these are first order. First order means it only works with the first order grade, I mean the gradient, it does not use Hessian, and that is what it means. Okay. So, numerical optimization mostly, as I said, mostly first order. Okay. So, basically A is what I was looking at, A t plus 1 is equal to A t minus eta grad with respect to A log A t. This is gradient descent. This is what you will see again and again and again in this course. Okay. You will see modifications over this, but this will come back again and again. This is basically the update rule using gradient descent. Okay. So, this is update rule in gradient descent. Okay. So, as you can, what are the things that you can understand from this equation? First of all, you can easily follow by t plus 1 and t that it is a iterative approach, right. Second, you can understand that only the gradient information is needed, right. Third, you can understand that gradient is always evaluated the previous step. So, there is no, I mean, iteration within iteration, there is no nested loop, for example. So, these are the three things you can potentially understand from this. What you do not know or what I have not yet defined is eta. What is eta? I have not defined that. So, eta in optimization term is known as step size. In machine learning sense, it is called learning rate. They are same. So, it is called step size in optimization, and there are ways of finding the optimal step size also. But in machine learning, at least in gradient descent or stochastic gradient descent, that will come later, this is generally what we call hyperparameter. Now, hyperparameter is a term I have not yet used, so I am using it for the first time in this course. So, can someone tell me what is hyperparameter?
We have the liberty of choosing.
Hmm?
You have the liberty of choosing it and finding which one is to fit this.
Right. So parameters is what? Parameters are the one that you train. So your A, for example, is a parameter. You are training it. Hyperparameters are also parameters, but you don't train them. You try to find the optimal configuration, often using validation data. So these are parameters that you are not training for, but you do need to optimize them or find some optimal configuration for them. Any hyperparameter that we have come across apart from eta till now in this course? Maybe I have not told you so, but is there anything that we have come across? Number of basis function. P is a hyperparameter. In fact, the basis function type, I use basis function, but should I use x square? Should I use sin x cos x? That's a hyperparameter. We are not optimizing for that. That is another one, right? So number of bases and type of basis. These are two hyperparameters that we have already discussed without using the term hyperparameter. And now there is a third one that I am introducing, which is eta, which is the learning rate. So this is my, as I said, step size. Let me write it at least once. I should use the proper optimization term. Anyways, I am going to use learning rate for the whole course, but at least once I should use the proper term. Okay, but aka learning rate. Okay. One more question. Why is there a negative sign? How can you provide me some reason why it should be negative and not positive? Don't say it will minimize. That is the, I know it will minimize, but why negative minimizes is what I am asking.
So the gradient will
So it is, remember that gradient is a vector. And if it is a vector, it will have magnitude and direction. That's the property of, that's the definition of a vector. Now the direction of a gradient vector is away from the minima. So because it is away from the minima, you give this negative sign to make it go towards the minima. So that means if I am maximizing, then I want to go away from the minima, then in that case that will become a positive sign and we will start calling it gradient ascent. So gradient descent is for minimization. The just change the sign, that becomes gradient ascent, it is for maximization. Okay. Now this question is not all for all, but if you can answer, this will be interesting. Any place where you use gradient ascent in machine learning? Can you think of a case study where we will use gradient ascent and not descent? Don't say I'll make a ALS minus ALS then use. Then that's not the answer, right? Maximize likelihood. If we work with likelihood and try to maximize it in that case, right? But anyways, we'll come to that later, but because we are here, I thought as a spoiler, let me give it to you. Okay. Okay. So this is the indirect way of solving or of equation 2, which is this one. And this is your step 3. Step 4, I will not even care to write, you will just use equation 1 and make predictions. So in general, in supervised learning at least, also in most unsupervised learning, there are 4 stages. Stage 1 is data collection. If that is given to you, you don't care about step 1 and go directly to step 2, which is model selection, right? Step 3 is training, which is the most expensive, most involved step. And lastly, prediction, deployment, inference, whatever you call it, right? So these are broadly speaking the 4 steps that will come again and again. Again, these 4 steps will keep on repeating throughout this course. Okay. Okay. So now we started talking about hyperparameters. So let us go there. Okay. Not to hyperparameter exactly, but rather a question: how to select what phi to use. How to select what basis function to use in equation 1. Any idea how will you select it? One was based on validation data, but that is probably not the optimal way of doing things. You have to do a lot of trials. So is there any way? I am not saying number of bases, keep in mind. I am only saying how to select what phi to use. How many phi? I'm not even going there.
So the training data will tell us, give us an idea.
How? I mean, you are in the right direction. That can we? I mean, probably what you are suggesting. If I rephrase it, the question or the solution might be that can we somehow infer phi from the training data? Right? Training for phi might be difficult. I mean, there is so many families of phi's that might not be possible, but still the question is, can we somehow infer or say something about phi or learn phi even from training data, right, during the training process itself. And obviously, I am and you are not the first one to think about it. People thought about it in 70s, 80s, and naturally, two classes of algorithms emerged from this question. The answer obviously is yes, and there are two classes of algorithm that emerges from this. Okay. So, another way of writing this question is, can D, for example, tell us something about phi? Okay. So, this is the same question posed in a different way. As I said, there are two school of thoughts, I will say broadly, that came out of this. The first school is the kernel based approaches. So, there is this kernel based approaches that you do in machine learning course. We will not do this, I mean, we will not talk about kernel based approaches in this course, but there is this support vector machine, for example, there is this Gaussian process. So, these are methods where you use kernel, and the kernels are represented in terms of data. And so, the idea is that kernel is an alternative to, let us say, basis function. For example, if you use a squared exponential kernel, you can mathematically show using squared exponential kernel is like using infinite number of bases, for example, right. So, one school of thought is kernel based approach. Again, this is covered in a usual machine learning course. We will not cover it here, but SVM, for example, or SVR, for example, is a good example, is a popular example for kernel based approach. Okay. The second one is learning the basis by bringing non-linearity into the system. Non-linearity in parameter, not in basis. Basis already is. The second one is learning basis by introducing non-linearity. And I am sure some of you might be wondering that basis function was non-linear already. So, what do I even mean when I say learning basis by bringing non-linearity into picture? So, bear with me for some time. Hopefully, by the end of this today's lecture, we will be at this point and we will be answering this question. Okay. We will not answer this question right now, but what I will tell you as a spoiler is one example of this is artificial neural network or neural network. Okay. So, example of this is artificial neural network. Artificial neural network does this, which means we will be talking about this. Okay. And how it happens will hopefully be answered by the time I finish today's lecture, which is maybe in another half an hour, 40 minutes or so. Okay. In fact, that is where I want to end today's lecture, by answering this question. So, the rest of today's lecture is about answering this question, okay, without trying to answer this question. Okay. Any question? Because this concludes the linear regression review part. We will proceed to neural network in some sense with this, but yeah, this concludes the linear regression. Any question on this part? I'm again, most of you have already studied this. This was repetition, at least for the UGs. This is a repetition, but yeah, if there is no question, we will proceed further. This question is not yet answered. How? We will come back to this when I start talking about neural network. Okay. Okay. So, moving ahead then. So, we start talking about neural network, which means the review is over and we are now into not yet into deep learning, but very close to starting deep learning. Okay. So, what is the idea of neural network? What is neural network? Not machine learning in general. Network of neurons in our brain. That is what a neural network is. So, why this name of, because this is motivated from how human brain works, at least loosely. Okay, I will not say very strongly, but loosely. Okay. So, neural network, the name came from the fact that this tries to mimic the neuron behavior in human brain or in general brain. Okay. So, tries or rather motivated from, right, to mimic operations in human brain. Okay. So, now how does human brain, what is the operation in human brain we are talking about? Any idea? You remember in biology neuron has different components, dendrites, axon and all of those things. So, how does these neurons operate?
It will fire when the threshold level of
That will come later, you are right, but that will come later. First, why this dendrites collects information from the axon of the neighboring neuron. So, information is collected by the dendrite from the axon of the neighboring neuron, right? And that and there are multiple neurons, right? And that information is accumulated. So, the first step is accumulation of information. So, you collect information and accumulate those, okay? And then as Harpreet was saying correctly, that then you check whether that accumulated information crosses a threshold or not. If it crosses a threshold, then the neuron fires. So that firing means passing information. Firing means it gets activated. So this term activated will become very important. Okay. So if the threshold is crossed, then the neuron is activated. A neuron getting activated means it will now pass information to the next neuron. If it is below the threshold, then it's 0. So it's not activated. And now there is a network of these things passing information in this manner. So there are 80 billion neurons in human mind, for example. Okay, and they pass information in mostly using this phenomena. So you accumulate information from the neighborhood, right? And then you accumulate information, then you check with the threshold. If the threshold is exceeded, you pass the information ahead. Otherwise, you don't. Okay. And then obviously, this is a very basic way of thinking. You can also think about plasticity, permanent changes in human brain neuron. You can think about memory leakage. So, all of things can come into picture, but in a very basic way, this is how it operates. Okay. Okay. So, let me write it down, right. So, broadly, neurons in human brain or neurons in general, not be in human brain also. I mean, it can be a jellyfish also. Human brain collects information from neighboring neurons, okay, and only passes that when a certain threshold is exceeded. Okay. And there are two terms here that I would like you to focus on. One is collects information. Okay. This is accumulation. and then there is this threshold. These are the two parts that we should that we will discuss in more details. Okay, now. So, now this is how human brain works. So, the idea in artificial neural network is that can we bring this idea or use this high level idea to develop model, machine learning model that hopefully will perform well. And all of this came from the fact because remember the definition of AI I was talking about in the first lecture. So, one of the thing was acting like human. So, if you have to act like human, you need to mimic human. So, this is one attempt, early attempt in that direction. Okay. So, this comes from the fact that artificial intelligence, human beings are intelligent. If human beings are intelligent, we want machines to be as intelligent as human. So, we should mimic what human does even at a cellular level. That is the motivation. Okay. Okay. So, collection of information, right. So, the first thing we need to talk about is accumulation. Collection. Okay. So, how do you think these neurons in our brain, I mean collect information? What does accumulation means? It means collection, but does it collect it as it is or does it combine it? If I give you 5 informations, your brain and you in general will not give equal weightage to all of this, right? If I tell you something about discourse, maybe you will be more careful, but if I tell something random, you might not remember those things after two days. So, which means not all information is equally weighted. So, when you are accumulating things, not everything is equally important, right. So, which information is how much important is something that is to be learned somehow, right. So, noticing this, so accumulation, collection, one way of modeling it, maybe the easiest way of modeling it is as follow. Z is the accumulated information, and let us say I have k neurons. Okay. So, then this becomes summation I equal to 1 to k wi and xi. Looks like linear regression, right? It is linear regression. Okay, it is linear regression. So, what is my xi? This is the information from ith neuron. Okay. What is wi? Weightage, and this is the accumulated information. This is accumulated information. Okay. So, you are taking this information, accumulating it using weights. Obviously, there can be some bias also. So, you can also add that. Let me add that plus b, let us say. Okay. So, b becomes my bias. Okay. So, this you can imagine, right? Why am I calling it accumulation? Why the W's are coming, why the B is coming? B because even before any information we might be biased towards something. So, that is why it is bias, right. Now, this is linear regression. So, if I draw comparison with linear regression, the feature vectors or the features, right, x1, x2, xk, those are like my neurons, neighboring neurons. They are sending that x1, x2, xk as information. You are accumulating them as summation wi xi with some bias also. So, this is linear regression, but there is one more operation here, right. The second operation is threshold is exceeded, right? Which also means, this also means activation, right? This is talking about whether it is getting activated or not. So now for activation, that is the second step, right? So activation operation, you can think of it as y, which is now what will the output will be, is equal to sigma z, and this controls whether it's activated or not. It controls whether it is activated or not. So mathematically, what is sigma? Huh? Step function. It's a threshold function. If certain threshold is considered, is exceeded, you activate it. So output becomes 1, let's say. I mean, binary spikes kind of thing. If it is less than the threshold, output is 0. Okay. So this is equal to, I mean you can write it something like this also. 1 if z is greater than some z threshold and 0 elsewhere. Okay. So this is the threshold function, and this was the by the way, this is a name, by the way. What is the name in neural network? Sigma is activation function. This model y is equal to sigma z, perceptron. So in neural network, this is known as the perceptron. So this perceptron model was the original model that was motivated from the working of human brain or neurons in general. Okay. So this is the perceptron in general. Okay, a perceptron unit rather is the correct terminology, where you accumulate the information and then you see whether the threshold is crossed or not, you get 1 or 0. Now, if the output is 1 or 0, what do you think perceptron was used to solve? Binary classification. Perceptron is 1 or 0, right, output. So what can it solve? Binary classification, male versus female, pass versus fail, safe versus unsafe. These are the problems it will solve. It is not for regression, for example. How will you solve regression? It can be, but then there is you need additional post processing in that case. Okay. Otherwise, it was originally for classification, which is fine. Right? So yeah. So the idea is, let me repeat. So broadly, neurons in human brain collects information, and that is the accumulation operation. And then the accumulated information, you check whether a threshold is exceeded or not. If it is exceeded, it fires, gives 1. If not, it does not fire, that is 0. Okay, and that's what it is. Now that operation, when you write into mathematical form with xi as the information coming from the neighboring neuron is equivalent to your feature, w, the accumulation weight, is equal to your learnable weights, b, your own bias is equal to some bias in your model, and sigma as some threshold function because fires or not fire. Then you get a model which is shown in this equation that you see, and this is known as perceptron. Okay. So perceptron, and in perceptron you have what? Z is equal to W transpose X plus B, right, in vector notation, and then your Y is equal to sigma of Z, right. Y is equal to sigma of z, where sigma is my threshold function. Threshold function. Okay. Clear? Now, how do you represent it? Let us also represent this thing. So, let me try to draw, and I'll draw a very bad useless diagram of the original human neuron first. Okay, I'm quite sure of that. I am very confident about my own drawing. It will be very bad, but then hopefully from that I will draw the diagram that we'll use in this course of a neuron model. Okay, so if you think about the neuron, I think something like this the neuron looks. Again, a very bad diagram, but that's okay, I guess. Okay, and obviously from each of these you will have different neurons going which are connecting, right? So in this manner, right? This, so information comes from this. Okay, and this orange line that you are seeing is the accumulation operation. So basically these are the information coming, and then this dendrite will accumulate that information. Okay, and then there is a threshold function somewhere sitting here, and if that threshold is, sorry, 1 second, yeah. So then if this threshold function is sitting there, if that threshold is exceeded, then the information can pass and the axon can pass it to the next neuron, right. So there is this accumulation operation in orange, then the threshold function also in orange, and the green line is only there if the threshold is exceeded. So similarly, now the artificial neuron, which hopefully will be better. So you have what? X1, X2, Xk. Okay. These are my features. Each feature is a node, neuron. Okay. And then there is this operation. Okay. All this will go here, and your output will be y. So this is the compute unit. The middle circle is the compute unit. What is happening inside the compute unit? Two things: accumulation and thresholding. So which means, first what is happening? Accumulation. Summation is represents accumulation. So your W transpose X plus B. And then there is this activation. Okay. Each of these X1, Xk are your input features to start with. They are accumulated using the summation operation, and then there is this threshold function, and yeah, and that gives you your y. Okay. But perceptron is not, I mean, perceptron has one at least major issue, if not more. Can you guess from whatever we have discussed till now, what is the potential issue that is there in perceptron?
Either takes the information or.
Correct, but why is that an information? Why is that an issue? That is true, and that will result in the issue, but what is the issue? Think about the 4 steps we talked about earlier. First was data is given to us, don't worry. Second is the model. I just wrote the model, I mean, this is my model. So model is known. Third is training. Fourth is prediction. So first two we have already discussed. So now the third and fourth, one of these should have an issue. So what is the third step? Training, how will you train this model? How do we train any model? Optimization. So we'll define a loss function. Let's define a loss function, okay? And then what do we need of the, what do we do with the loss function? Minimize. For that, what do we need? Derivative. Now, if we try to take derivative of this, what will happen? Not differentiable, it's a delta function. At the point the spike is happening, it is infinite. Everywhere else, it is 0. So you can imagine that this, can you now train the model? You can tune the model manually by trying certain things. Hopefully, you can use some gradient free methods to do a broad search to find something. But definitely, you cannot train the model using gradient. That is a problem. We are not able to train the model. That is a big problem, right? So, in perceptron, the sigma is non-differentiable. Right? You cannot differentiate sigma, which means obviously direct method or indirect method, none of that can be used. Neither direct method nor indirect method can be used. Okay. And just to make it mathematically rigorous, let me also write the equation and show you exactly where the problem will come. Okay. So, what is the loss function in this case? Just to make it concrete. Let us take any loss function, let us take the mean square loss, because if I take the other loss, then also at one point it is, yeah, discontinuous in some sense. So, let us take the mean square. So, L W comma B, W comma B is my trainable parameters. We will start calling it theta very soon, but for now it is W comma B is equal to, I have the same n data points, summation I equal to 1 to n, and then I have yi minus sigma W transpose xi plus b square, right. There is one change, by the way, I just realized. We should call it y tilde, by the way, because y is my measurement. This will not match exactly, so we should call it y tilde. Okay. So, while I was writing it, I realized that messed it up. So, anyways, and here keep in mind that this is my, what is this? Z, and this is my y tilde. I should also write, right. Okay. So, now if you have to compute the gradient, right, and let us take only W, I mean, because I will not compute the gradient completely. So, can you tell me how will we proceed? We will use a chain rule, right, chain rule, right, del L by del, sorry, del L by del y tilde del y tilde by del z del z by del W. Basic chain rule, right? Correct. Now, the first one, del L by del y tilde, is that a issue to compute? It is squared, right? 2 times that thing will come, right, with a negative sign. The second one, del y tilde by del z. Is that a issue? It is. Y tilde is equal to what? Sigma times z. It's that threshold function. So the second term is the issue. Third term, is that a issue? No, it's linear regression term. So the first and third term are okay. This is the second one is the problem term. This one is the problematic. Okay. So no, not everything is good. So what happened then was people thought that can we somehow, because threshold function people were very attached to, because there was evidence that human brain works in this way. What evidence was there? Even that's a different story, but so there is this Hodgkin Huxley, there were 2 researchers who studied neuron activity in jellyfish and came up with an equation based on that, and that clearly shows the behavior. And in fact, for that they received Nobel Prize around 1961-62 in around that. So Hodgkin and Huxley received Nobel Prize for developing the neuron model from a jellyfish, and that shows that it's a spiking behavior. So if it's spiking behavior and we are going by the assumption human are intelligent, we need to mimic them. So naturally, at that stage, at least, people were still attached to threshold function, but they could not use the threshold function in practical problem, right? So what was the solution? They did the next best thing. Can we make threshold function smooth? Okay, and that gave rise to the sigmoid activation. I mean, that naturally goes to the sigmoid activation. So threshold function, let me draw it. So threshold function is like this, right? This is my threshold function. Sigmoid function is this. So you can imagine that it's an approximation of the threshold function, but now with this, it's you can compute a derivative. So this is my sigmoid, this is my threshold. And what is the formula for sigmoid? So sigmoid is basically so sigma of z is equal to 1 by 1 plus exponential of minus z. Okay, so this is my sigmoid function. So instead of threshold, sigmoid came into picture. Sigmoid, you can see there is an exponential setting. You differentiate it as many times as you want, no issues. But is it so? Do you see any issue in the diagram? From the diagram, do you see any issue? There is. Look at the, so you see gradient. Gradient was the issue, so you should check the gradient. So what is the gradient here? You see at z goes beyond a certain number, and not very large number that is, or below a certain number on negative side, what happens to the gradient? Very small, 0. So sigmoid activation has the problem known as the vanishing gradient problem. So in this activation, what happens? The gradient starts vanishing. So you cannot go far away from on the either side. It's symmetric, so on either side. So sigmoid was a close approximation of this threshold, but vanishing gradient problem. Okay. So however, this has vanishing gradient problem. Vanishing gradient problem means the gradient goes very close to 0. And why is that a problem? Well, look at the equation. What will happen if one of the terms goes to very close to 0? Whole thing goes to 0. What happens if the whole thing is equal to 0? No update, right? Where is it? I wrote it somewhere. I think above, right? Yeah. Yes. So if the gradient is 0, the second term is 0. So Wt or At plus 1 is equal to At. No update. So whatever random guess you take, if that goes there, you are there. You are not moving anywhere. That's a big problem. Okay. Clear why vanishing gradient is a problem? Okay. So vanishing gradient is a problem. By the way, in between people also tried that, I mean sigmoid was non-negative also. So there is a, people tried using tan hyperbolic also. Tan hyperbolic looks exactly like sigmoid. It's just a scaled version. So you just pull it in this direction. The 0.5 in the middle becomes 0. The 0 thing becomes -1 and it becomes symmetric. So tan hyperbolic is a scaled version of sigmoid. You can prove it. But the problem stays. Even with tan hyperbolic, it's infinitely differentiable, but it also has the vanishing gradient problem. So there is also this idea of tan hyperbolic, it has also the vanishing gradient problem. And by this time people started exploring other activations which need not be like the threshold function. Remember, tan hyperbolic and sigmoid both are like the threshold function, at least in some sense. But by this time people realize that this problem is coming again and again. So maybe we can move beyond this threshold function. And I personally believe, it is not written anywhere, my own thoughts, that it also came from the 4 definitions we discussed. From acting like human, the other definition that became popular was acting rationally. So human being is not the epitome of intelligence. It is possible that someone might be more intelligent. Something, I don't know what that is, but yes. So other activation functions starts coming into picture. By the way, right now there is around, I read one paper where there was around 180 activation functions. So you can imagine that people are still proposing new activation functions. Obviously, I am not going to discuss about 180 activation functions, but so then obviously after some time, ReLU came into picture. ReLU basically is this and this, where that means sigma of z will be equal to z if z is greater than 0, 0 elsewhere. Okay. But with ReLU, you can see the dying ReLU problem. It's known as the dying ReLU problem, that on the negative side, the output, there is no output, gradient also is 0. So not only zero gradient, 0 output also. So that's why it's called the dying ReLU problem. Okay. So it has the, this portion has the dying ReLU problem. Dying ReLU means no output, also gradient 0.
It's also not differentiable.
Huh?
It's also not differentiable.
At that point it is, yes. So it's not exactly differentiable, right hand and left hand does not match. So but there is some idea of this subgradients that is used. So there is this idea of subgradient that you can use, where right hand and left hand does not match, you take the better one, which is the right hand, and work with that. Okay. It is true, at 0 it is not differentiable. Right hand and left hand derivatives does not match. Okay. But the problem with threshold was that it's not, I mean right hand, left hand, everything was 0. So there is no right hand and left hand, and at that point it is infinite. So that was even more severe, right? Okay. So dying ReLU, why dying ReLU? Because that portion is 0 output, 0 gradient. So it is kind of dead. It's neither breathing nor moving. That's why dying ReLU. Any question? I have what, 4 minutes, 5 minutes. Okay, I want to reach that point. So so I will just specify that apart from ReLU, I mean to address this dying ReLU problem, there is this leaky ReLU, there is this ELU, there is this GELU, and now there is also MIS and many others. As I said, there is 180, right? So, but dying ReLU, sorry, the leaky ReLU at least I should mention. And this took us to leaky ReLU. Leaky ReLU said that okay, it is dying, I will not let it die. Okay. So, it is now not dying. It was dying, so it is not dying. It might be very old, so the gradient is very small, but at least not dying. There is some gradient, there is some small value, no, and that's some alpha gradient, right? So this is the leaky ReLU. I am not writing the equation, but can you guess what is the equation for leaky ReLU? I will show you the equation for ReLU. See, this is the equation for ReLU. What is the equation for leaky ReLU? Yes, alpha times z. Okay, where alpha is 0.01, 0.001. Take some value. So leaky ReLU, as correctly pointed out, z alpha z elsewhere, and then alpha much less than 1. Okay. Last thing for today, and this is the point again where I will start next time. So whatever we discuss for next 2-3 minutes is where we will start next time. So remember, in all of this, what we have done is that we are using one unit, right? This diagram is one unit, it's a neuron. But human brain does not work with a single neuron. It works with network of neurons. So that means one of this is potentially not enough to express functions. So can we make it more expressive? And the idea, how do you make it more expressive? Well, one of the ideas is that stack multiple of this over one another. So one neuron is never enough. And I now am stressing the term never because I mean that it is not enough for human, neither it is enough for machines. So in that sense, right, philosophically. So one neuron is never enough. So we use multiple. So remember, we have this x1, x2, xk. Now instead of one, I have multiple such units. So and then comes my output. Okay. Remember, each of the middle circles that you are seeing is actually this one, the middle one. Each of that is this one. So each of that has a sigma operation, has a summation accumulation operation. So instead of one, you are now using multiple of those. And not only that, you are also then, because there is multiple, you need to bring it to one. So after using multiple, you are having one more layer kind of thing, which is bringing it to one. Okay. So now, if that is the case, can you tell me what this equation, let us say this output is H. So what will be H equal to in terms of X? This is H. So not to, let us call it, this is H1. So what is H1? H1 is equal to sigma W transpose X plus B. B I have not shown, but B is also there going, okay. B I have not shown here, right. It is H sigma W transpose X plus B, right. H2 is same thing, but W1, W2, that B1, B2, that will happen, okay. So let me write W1 and B1, and now you can see H2 is sigma W2 transpose X plus B2. HP, for example, is, so let us call it P, right, HP. So HP is sigma WP transpose X plus BP. Okay. And now what is Y? What is Y? This is Y. Tell me the equation for Y. Sigma, I am not writing sigma, let us say, then I can write sigma, but let us say sigma is not there. W, I will write it A because W I have already used. So A transpose H plus B I have used, so let us call it BA. What is this equation without sigma? Linear regression. What is H? Basis function. How are you getting H? From the input through the data, because W and B are learned. So is it not that the first layer is kind of learning the optimal basis from your data, and then those are combined to give your Y? Remember the second point I said? You were saying something? Okay. Remember the point I said earlier, that the second way is that can we learn the basis by introducing nonlinearity? The nonlinearity is sigmoid or ReLU or GALU, whatever, right? And we call it activation function from its own source, original source, which was that human brain activates, so the name stays. But for practical purpose, what is activation function? A nonlinear function, right? So activation function is a nonlinear function. We introduce nonlinear function, and that allows us, the first layer is kind of learning the basis function, hopefully optimal basis function, and then those bases are getting combined in a linear way to get Y. Now someone was saying sigma, there can be sigma as well, but for regression problem generally that sigma is linear. So no activation is linear activation. Okay, clear? So we'll start from this point next time and then okay, thank you.